In the previous video, we talked about how the atomic mass unit and the mole are based off of fractional values of the carbon-12 atom. But if you look at the periodic table for carbon, you'll see that the atomic number, as predicted, is 12, but the atomic mass of carbon at the bottom of the box you'll see is not 12, but rather 12.011. What? What is the mass of carbon? Well, this is why we talked about isotopes in the previous class. Even though we've based our standards for atomic mass on carbon-12, it turns out carbon-12 isn't the only type of carbon that exists in nature. We also have carbon-13 to deal with. The periodic table contains the average atomic mass for the element, which takes into account both the mass and the relative abundance of all the naturally occurring isotopes for a particular element. So for carbon-12, the mass on the periodic table isn't just the mass of carbon-12. It's a weighted average of the different isotopes and the frequency at which they occur in nature. Take a look at this table below and practice your atomic notation skills to fill in the number of protons and neutrons. We can see here that the atomic mass of carbon-12 is 12, and 12 AMU, and it has a natural abundance of 98.9%. So if we were to take a hunk of elemental carbon out of the ground, it would be 98.9% carbon-12. However, the remaining 1.1% of carbon is carbon-13, which is 13.00336 atomic mass units. You'll become familiar with carbon-13 in organic chemistry. I've also included carbon-14 in this table, which is radioactive. Now, the amount of carbon-14 is so small that we don't include it in our calculations. However, there is enough to not make a difference in the average atomic mass, but to still be quantifiable by radioactive assays, specifically carbon-14 dating. We'll include it here for information's sake, but you won't include it in your calculations since we can assume it has a negligible contribution to the average atomic mass. What I'd like to do now is to take a minute and see how we arrive at the value for the average atomic mass of carbon that we see on the periodic table. We'll try two methods, an average and a weighted average, and see which one is correct. So, let's go ahead and start taking the average of the two isotopes of carbon. Take a minute and try it on your own. So when we take the average, we get a value, 12.5 AMU, that's higher than what we see in the table. Now there must be something else going on. Why don't you try taking the weighted average of the two isotopes? If you need a little help with calculating the weighted average of the isotope, I'll show you how now. So what we'll do is we will take the atomic weight of one isotope, so we'll say isotope A, and we will multiply it by the natural abundance, and then we'll add it to the atomic mass of element or isotope Y times the natural abundance of isotope Y, and that will give us the average atomic mass. Now, the formula that we are having here needs the fractional value or the ratio of the particular of one element over the total. However, in the table, we have the natural abundance in percentage. So in order to convert our natural abundance into decimals, we'll want to divide by 100 to get 0.989 and 0.0011. So now that you know the atomic mass units of each and the fractional natural abundance for each, why don't you take a stab at the weighted average? All right. If we plug in the correct numbers into the formula, so 12 AMU times 0.989 plus 13.00336 AMU times 0.0011, we arrive at 12.011 AMU, which is the average atomic weight that we see in the periodic table. Good work, team!